Sensitivity, latent image, and development. Primary processes. Two opposing theories of the latent image exist. 1. According to the silver halide theory, the latent image is formed by a change in the silver halide itself, i.e., by the formation of metallic silver, so-called photosilver. More will be said later as to how far this photosilver is equivalent to the latent image. 2. According to Renwick's theory, at least in highly sensitive emulsions, preformed silver particles are changed by light from a sol to a gel form, and in this way, nuclei for development are obtained. Furthermore, F. Weigert has built up a micelle theory of the latent image from his experiments on induced optical anisotropy, according to which the latent image must be formed from physically changed micelles, dense yet amorphous aggregates of molecules of all constituents of the emulsion, the original silver dye, silver sulfide, and the silver halide itself. The change on exposure to light, which represents the spatial orientation of the micelle elements, corresponds simultaneously to an increased catalytic activity towards the developer. The author cannot agree with Weigart's theory for two reasons. 1. The spectral sensitivity of a silver halide corresponds fairly accurately to its spectral absorption as shown by Hughes and Muehlendijk and by Toy and Edgerton. 2. The author has been able to prove that desensitizing with chromic acid does not alter the spectral distribution of the sensitivity at all, although certainly in this way the primary silver micelles are destroyed. There is also direct proof for the existence of the photosilver. A. According to Toy and Harrison, the primary process of photoconductivity of silver bromide is comparable throughout to its photographic effect. B. In the experiments made by Shepard and Vensilo on the photovoltaic effect of silver-silver bromide electrodes, it was proved that photoelectrons and bromine atoms are set free synergically. The results may be considered as a good confirmation of the assumed process, which is followed by the photographically important reaction. C. The first measurements on the spectral absorption of silver halide crystals were reported in 1930 by Hilsch and Pohl. Comparison between the alkali halides and the silver halides showed that the former gave moderately sharp but continuous bands. It is noteworthy that not the long wavelength limits, but the maxima proper frequency of these bands are represented by energy equations. Our values agree well with those of Hilsch and Pohl for the alkali salts. With the silver halides, the conditions are much more complicated. The maxima or proper frequencies are not sharp, but are barely distinguishable. According to Hilsch and Pohl, with alkali halides, for each halide a single band is obtained, which is separated from the absorption spectrum of the crystal lattice by a wide region free from absorption. A single reaction product corresponds here to a single absorption process. In the first case, this product will be formed from simple, neutral alkali atoms. According to the classical dispersion formula, the number of color centers can be computed and compared with the absorbed light quanta. In this way, Smakula obtained values between 0.6 and 0.9 as the yield in alkali halide crystals. Hilsch and Pohl found values of 0.4 and 0.33 for silver chloride and silver bromide, and noted that these values approximate the quantum equivalent in the exposure region of the latent image. The investigations on photoconductivity, photoelectric effect, and light absorption of crystals and of the photoproduct all lead to the same conclusion. The primary photochemical process in the absorption of light by silver halide crystals, even in the region of the normal latent image, consists in the release of electrons from bromide ions and the acceptance of these electrons by silver ions. The course of this decomposition has not yet been completely explained. As shown, and as seen in Table 2, the simple energy equations are insufficient to indicate the absorption regions in the case of the silver halides. Developability. Relation between photochemical and photographic sensitivity. According to earlier results, photochemical sensitivity does not bear a definite simple relationship to photographic sensitivity. Otherwise, the same light absorption in the same silver halide should always give the same photographic effect. This is not the case, however. Two silver halide emulsions, which contain exactly the same amount of the same silver halide, identical in grain size and dispersity, may show considerable difference in photographic sensitivity. In relation to this is Treveli's proof of the statistical distribution of developability among equally exposed grains of the same size. Furthermore, with X-rays, each absorbed quantum makes one grain developable. The absorption of such an enormous quantum causes decomposition of the atomic nuclei, setting free many electrons and light quanta. An absorption yield of up to 1,000 silver atoms per quantum was found by Eggert and Nodak. Such a large aggregation of silver atoms appears in every case to provide a nucleus for development. On the other hand, with ultraviolet and visible light, where not more than one silver atom is found for each light quantum absorbed, the number of atoms required to make a grain developable depends on the state of the grain and particularly on the so-called ripening nuclei. Ripening nuclei. The importance of ripening nuclei has been discussed by Eder and Lupo Kramer. Usually it is assumed that they are caused by a slight reduction to silver, which agrees with Lupo Kramer's discovery of desensitizing by chromic acid. Some observations of Shepard, Treveli, and Whiteman make this appear doubtful. They found that the sensitizing nuclei showed much greater resistance to chromic acid, etc., than did the latent image for the same emulsion. In agreement with this, W. Clark showed that a preliminary exposure greatly increased the desensitizing effect with chromic acid. This difference in behavior of ripening nuclei and latent image must be attributed either to different substances or to different states of combination. The marked dependence of the formation of ripening nuclei on the kind of gelatin was shown by Shepard. In a fairly extensive investigation on the manufacture of gelatin, Shepard and Hudson found that A. Certain kinds of gelatin were sensitized by the addition of ethyl or petroleum ether extracts obtained from hides or the seeds of certain plants. B. Substances were found in all these extracts which precipitated out silver sulfide from ammoniacal silver oxide solutions. C. Pure substances containing sulfur, such as thiocarbamide, thiosulfate, and especially mustard oil, also showed this sensitizing ability. Shepard concluded that the ripening nuclei must consist in part of silver sulfide. R. Luther and Menkenberg independently discovered the sensitizing ability of silver sulfide nuclei. Later it was also found that suitable quantities of silver selenide and telluride can form sensitizing nuclei, while Leisgang showed that silver phosphate apparently has this property. The possibility that silver sulfide and silver sensitized jointly was discussed earlier by Shepard and Punnett, with the U.S. patent number 1,623,499. Silver value. Following Schmidt and Pretzschner, we were able to confirm the statement that large quantities of silver are obtained by treating emulsions directly with dilute nitric acid, but this, quote, silver value seems to be dependent on the method of washing. Schmidt and Pretzschner, as well as B. Carroll, have recently confirmed the splitting off of silver ions or silver oxide in acidified gelatin silver salt media. Luhr and Weigert, with fixed plates, obtained electrotitrimetrically primary silver values which have been sharply criticized and which will be mentioned later. For confirmation and evaluation of the silver sulfide nucleus theory, the application of a microanalytic method for determination of labile sulfur in gelatin, as well as of silver sulfide in emulsions, was exceedingly necessary. Such a method, depending on conversion to methylene blue, which is determined colorimetrically, was developed by Shepard with H. Hudson and A. Ballard. 1 part of silver sulfide in 2.10 to the 7th power parts of silver bromide and 10 parts in 10 to the 6th power parts of silver bromide can be quantitatively determined with an accuracy of approximately 5%. Luhr and Weigert conclude from the fact that their silver values tend to disappear on treatment with persulfate that it is silver and not silver sulfide. Shepard and Ballard were able to show that colloidally dispersed silver sulfide is dissolved by persulfate, although much more slowly than colloidally dispersed silver. Lohr and Weigart's primary silver, accordingly, may just as well be primary silver sulfide. The silver they find as primary silver is composed Lohr and Weigart's electrotrichometric method is thoroughly satisfactory. According to Schmidt and Pretzner, if neutral or alkaline solutions of sodium sulfite are used as fixing agent, then no determinable amount of extraneous silver is obtained. This was confirmed by careful control experiments. Also, we have not yet found any sign of a loss of silver. Since extraneous silver and a loss of silver disappear, then the total silver value of Lohr and Weigart is composed of the silver sulfide formed upon ripening plus the silver formed upon ripening, i.e. silver sulfide plus silver. Since Lohr and Weigart's electrotrichometric method can be determined by their methods, exact results can be obtained for the true silver. Nucleus theory and sensitivity. We are still a long way from a quantitative theory of the relationship of the nuclear material to sensitivity or to the sensitometric characteristics of silver halide emulsions. It can be shown that an excess of silver sulfide not only causes fog, but also reduces the increase in sensitivity originally affected. Sensitizing by nuclei of silver sulfide, silver, or silver sulfide plus silver is conditioned by a number of factors, including the dispersity, number, and position of the nuclei on the grain surface. It is concluded that, as distinct from optical sensitizing, normal sensitizing does not influence the primary photochemical process, but only its effectiveness in development. Lupo Kramer has shown that freshly precipitated silver bromide is immediately reduced in the dark by a developer, and that this reaction is inhibited by small amounts of gelatin. It may be assumed that the formation of nuclei by exposure acts against this inhibition. Photographic sensitivity then involves a balance between sensitizing and desensitizing factors. Nucleus action. The nuclei of silver sulfide or silver sulfide plus silver may be considered as heterogeneous catalysts for development, although colloidally dispersed silver and silver sulfide may also act as optical sensitizers under certain conditions. The fact is important that in this case, the silver may be replaced by silver sulfide. In this optical sensitizing, we are not dealing with scattered nuclei, but each grain is formed of an intimate mixture of colloidal silver or silver sulfide and silver halide. In spite of a much larger content of nuclear material than in normally ripened grains, these photolides do not fog. F. Weigart introduced the very important idea in his proof of induced optical anisotropy of developed image that the real action of the nucleus in development of the latent image is due to a specific orientation of the silver atoms. This idea, however, is not necessarily related to a missile hypothesis. In 1922, Shepard suggested an orientation theory of nuclear action and later worked out with Triveli and Loveland the idea that the catalytic effect of the ripening nuclei is purely topochemical. In any case, the photochemically formed silver atoms, photosilver, aggregate in the neighborhood of the nuclei. The cause of this aggregation can be explained in different ways. A decision between the different hypotheses is not possible at the present time. In the most common cases of heterogeneous catalysis, all that is known is the intermediary layer, quote, conductor/semiconductor or dielectric, end quote, facilitates certain electron transfers. It is possible to show experimentally that both silver sulfide and silver nuclei can behave as heterogeneous catalysts in other reactions involving silver salts. K.C.D.